So we'll start taking attendance, start from today. Make sure that you have video on for the entire 75 minutes if you want to get the bonus part. And also make sure that your name, your Zoom name is the same name as on Canvas. So the TA can put give the bonus, put the grade for you. Okay. Guess it's time. Yeah, we can get started. So in the last class, we talked about the stress. So basically, the general definition is internal force intensity. So it's internal force of area. Internal force is from statics. So that's why we keep emphasizing the important static for this class. Everything is built on the statics. You need to calculate internal force first, and then calculate internal force intensity, which becomes stress. So the simplest one is normal stress, which is if we have tension compression situation, then the normal stress equal to the internal normal force. Some tests will use P, some tests use N, doesn't matter. As long as you know that this is the internal normal force over the cross-section area. And to make a difference between this one and the shear stress, the normal force here is perpendicular to the cross-section area we use to calculate stress. So for the since it's force per unit area, if you have the SI unit, you have Newton per meter square. If you use the US customer unit, you have this PSI. And of course, we have the, make sure you mute the microphone. Thank you. Sign conventions. So the one shows here is the tension and of course we can do compression also. So no matter it's internal force or stress, the sign convention is the same. Whenever you see a tensile, it should be positive. Whenever you see a negative value, it should be compressive. Or back to this equation, you know that, well, A is just a constant. It's always a positive constant. So the stress, the sign of the stress and the internal force. And internal force should always be the same because this is just a always positive constant. So this is for stress, and this is the first example we did in class. And of course, this is similar situation we can think of because I mean, the first example is about like straightforward application of the concept. And key thing here, we need to figure out what is the internal normal stress in this section and internal normal stress in this section. And we need to make sure that both of them are lower than 150. First step, find the internal normal stress, internal normal force in the A, B, and BC. So since this is like a really at the beginning of semester, so I do this free bar diagram, this section and this section. But when we get later semester, we may skip, I mean, in the class, we may skip this class. We may skip these steps because for this one detention compression, it's really simple because let's say if you see this one, you know that internal normal force in the AB section should be 60, right? We probably can skip these steps. But of course, for this one, you need to really be careful, like what is the internal force? Remember last time we had really different solutions in the class. So make sure that you have it correct and also make sure that if it's compressive, you should have a negative sign. You should have a negative sign. So this is how we used to solve the diameter of the AB and BC section. And of course, this problem is simplified in the way that no matter its tension and compression, when it fail at magnitude of 150 megapascal. So that's why we are comparing the magnitude here. In real situation, if you learn something about the material science, you should know that for the most of the metal material, it can survive from larger compression than the tension. But this example problem just simplified. We consider the fail both at 150 megapascal tension and 150 megapascal compression. So that is normal stress. Shear stress, we also talk about the concept part is the shear force. This is the internal shear force. This is the internal shear force. So and this is the area. And this area is here, or on the backside here. So again, let me emphasize again. Now this area is parallel to the shear force. Normal stress, the force is perpendicular to the cross-section area, but here shear stress is parallel. So we need to figure out, using static, figure out what is the shear force and use the area, and we can calculate shear stress. And the thing here, we use subscript step average because the unlike the normal stress, the variation of the stress over the cross-section area is very small. We can kind of, as engineer, we can kind of ignore the variation, and we consider the stress is uniform distributed over the cross-section. But for the shear stress, the variation is not that small. We will learn in the later chapter that it's actually start from zero from top and bottom surface and maximum at the neutral surface. We'll talk about in detail in the later chapter, but here we just need to understand that the shear stress is not constant over this area, and we cannot consider it, it's constant. So that's why we use average. The thing we are calculating here is really the average shear stress. And sign convention is same as internal shear force. We talked about in the static review what is the sign convention for the internal shear force. So this is the same because again, back to the equation, as you can see that the only difference of shear stress and internal shear force is area, and area is always a positive constant. It's a positive value. So that is the definition of average shear stress. And we also, in the real application, we have the single shear and double shear. So this is a single shear situation. It's considered as now the V internal shear force here. If we use V here, then V equal to F. So it's F of A. But if the double shear like this, now you can consider the V equal to half of F. So that's why we have F over 2A. Or you can consider it as the force, the transverse force applied is carried by 2 area. Again, F over 2A. So understanding either way should be fine. So this is the conceptual part of the shear stress. This is the example problem we'll do today. So we have a wood joint, and this is wood joint, and the thickness, the width, 1.15. So that's basically in the plane direction. So let's say if this is X, this is Y, the 1.15 is the Z direction. Magnitude average shear stress along the plane AA and BBs. How to calculate the shear stress? Let's say for AA, what is the internal shear force on AA section? What is the area? What area we can calculate? What's the internal shear force on AA? Anyone? What's the internal shear force on along the plane AA here?
Is it 3 kilonewtons?
Yes, thank you. So since we have 6 applied here, so you should expect this one should be half, and of course half is carried by here. So the internal shear force on the AA plane area, AA plane, it is 3. How to calculate area? What area should I use when I calculate shear stress on the AA plane?
0.1 times 0.15.
Yes. Of course, I'm calculating the magnitude here. And for the BB section, how to calculate the shear stress on BB plane? What is the shear force?
Would it be 6 kilonewtons?
6. Why?
Because it looks like it's single instead of double. I mean, that's just a guess. I'm not really sure.
But it's a symmetric, it's also, there's a symmetric part here. Right. So it's very similar for this one. So let's say when you have, let's say if we do the free bar diagram of this thing, you have 6 here, so you know that I have 3 here, 3 here is symmetric about this axis. And of course, if we have 3 applied here, the same thing, this section applied to this outer structure is also 3, and 3 here. Right, it's symmetric. It's symmetric about this axis. So it should be 3. Is this clear? Any question about this internal shear force on the AA and the BB?
I'm confused on how for plane BB, the way I see it, I see my brain just sees 2 forces applied to it, but for the plane of AA, I only see 1 force. So I'm still confused on how it's still 3.
Okay, thank you for the question. Let me do the free bar diagram so it's clear for you guys. So let's say let's take this thing, the internal thing out and do the free bar diagram. And it's symmetric. We have 6 here. And we know that there should be a force applied here and here. It's again symmetric. And these 2 force, since it's symmetric, these 2 force should be the same. So let's use F. So the free bar diagram of this one is 6 minus 2F equal to 0. F equal to 3 kilonewton. Makes sense or not? Now the force applied, so this F and this F, you can consider is this contacting surface, the force applied by this outer structure to the inner structure through this contacting surface, right? And the same thing, the F here is the bottom part, the force applied by the outer structure to the inner structure at this contacting surface. And for these 2 forces, they are equal, they are symmetric, they are equal to 3 kilonewton. And for the shear force in the BB section, we can consider is the internal structure, inner structure applied to the outer structure, again, as its contact surface. So basically, they are the same magnitude, different direction. One is the force from applied by the outer structure to the inner structure. Why the force applied? Make sure you guys is echo or I don't know. Why is the force applied from the inner structure to the outer structure? They should be the same magnitude, opposite direction. That's why for the BB, shear force on the BB plane is also 3. Or I can do it in this way. So let's take this section. Let's cut this section off from the outer structure. So I put it here. And of course, this is a BB plane. And we want to figure out what the shear stress generate on this BB plane. So we already figured out that the force applied by the inner structure to the outer structure on this cross-section through the contacting surface is 3 kilonewton. It's force and reaction force. So there should be the same magnitudes of the direction. So to make sure that it's equilibrium of this small cut section, the V on this shear force on the BB section should also equal to 3 kilonewton in the opposite direction. That's how we figure out this one and this one. Is this clear or not? Or any question?
I have a question.
Yeah.
Are we divided by 0.015 or 0.125?
Are you which
For the shear stress of A.
it should be this area, right? So it's 0.1 times the width. The width is
Oh.
the dimension in the z direction.
Okay, I didn't see the width. Sorry.
Yeah, you're welcome.
Thank you.
So for the question in the chat, if you want to ask for the magnitude, A, B negative. So for now, now we're only focused on the magnitude. We talk about the sign in detail in a later chapter, including how it's distributed over the cross section, how it's distributed over the cross section, and what is the sign we should use. So we talk about in chapter 6, but for now we are calculating the magnitude because let's say for deciding if it's safe or fail, no matter it's shear stress in this direction or shear stress in this direction, as long as the magnitude exceeding allowable shear stress, it will fail. The sign right now, we can just ignore it. But we talk about it in detail in chapter 6 about the distribution and sign. Does the 6 kilonewton force on the left side imply the structure is not moving? This is a mechanics materials class. This is not dynamics. Everything in mechanics materials, they're not moving. They're in equilibrium. Force in equilibrium. I think you are talking about like F equal to M, F equal to MA. No, that's dynamics. Mechanics materials, everything should be in equilibrium. The force in the x direction equal to 0, force in the y direction equal to 0, moment about a point equal to 0. Yeah, you can ask.
Sorry, can you explain real quick why the 6 kilonewtons on the left doesn't affect this in any way?
That's not affect what?
That doesn't affect the equations in any way?
It affects us. You mean here?
No, like the 6 kilonewtons on the left side of the wood joint. The other one?
What is this? Oh,
No,
this one student told me it's this. I wrote here. Are you talking about this one?
no, I'm talking about on the other side of the joint. Do you see the 6 kilonewtons going towards the left? Like, why does that not affect anything?
on the other side. Oh, you're talking about this one.
Yes.
The whole structure is in equilibrium. Do you agree with me or not? So let's consider this is the entire structure. When you have 6 kilonewton here, do you agree that to make this one in equilibrium, you have to have a 6 kilonewton on the opposite side, opposite direction, so that the whole structure is not moving, it's in equilibrium, right? So yes, the free body diagram I'm doing here is considering only this part. And now we are only considering this one. Let's back to your question. I can also, let's say we have the outer structure. I'm not good at drawing things, but you know what I mean. Let's say, back to your question. If we consider this one and do the free body diagram of the outer structure, do you agree that this is 6 kilonewton? So to make sure this one also in equilibrium, there should be a force applied here. This should be a force applied here. And since it's symmetric about this axis, so the force here and here should be the same. Now let's put this force as F, this force as F. Again, we have 2F minus 6 equal to 0. Force in the x direction equal to 0. Now we have this shear force equal to 3. Make sense or not? Now we are taking care of this one.
That makes sense. Thank you.
You're welcome. I was curious how the 6 minutes on the left would not affect anything. Yeah, I think this one explained also the question in the chat. Sorry, just to be accurate, it's not about non-moving or moving. So it's move and the constant speed is also in equilibrium. The thing I think you guys say the moving or non-moving is acceleration is 0, non-zero, right? So in mechanics materials, everything is in equilibrium, A equal to 0. So are there any other question about the internal force and everything? Okay, now let's continue with this one. So we have the internal force on the BB plane is 3 kilonewton. What area should we use? What area should we use?
0.125 times 0.15.
Yes, thank you. Now we are done for this one. Shear stress, AA plane, BB plane. The next topic is the bearing stress. It's I would say that out of the 3 stress, normal stress, shear stress, and bearing stress, the most commonly used, they are the normal stress and shear stress. Bearing stress, we don't use it that much when you go to learn more in the solid mechanics class. But to be complete and also to be consistent with textbook, I also include bearing stress here. And I think it is good to understand what if you have a contacting what if you have a fastener and a fastener hole? What is the stress generated because it's contacting the fastener and the fastener holes? So this is the bearing stress. Just imagine that you use a fastener to connect 2 plates, and the 2 plates, there are tension exists on these 2 plates. So this tension in the plate itself for this plate itself, this tension compression is tensile stress, right? Tensile force, tensile stress. For the fastener, it actually becomes for the fastener, if we calculate the stress in the fastener, it is the shear stress. Do you guys agree? It's a shear stress generated in the fastener. And there's another stress exists. That is, you can just imagine the half of cylinder surface contacting with the fastener outer surface. There's a contacting stress. There's a stress generated because of this contacting. And this one is considered as the bearing stress. So we use sigma B. So the substrate B represents the bearing stress, and it's equal to, again, equal to P over A. And the A here, be very careful, it's not the surface of the half cylinder. If it's not the, so this is the fastener hole, it's not the inside surface of the half cylinder, it is the projected area. So it's basically, you consider its project area, so it's this rectangle. Because again, the distribution of this bearing stress is very complicated over the half cylinder. And for exact like how it's distributed over the over the outer surface of the fastener or the inner half circle surface of the cylinder, is very complicated. You will learn in detail in more advanced class, but in this class at the beginning of semester, let's just simplify as the force over this project area, and this project area is a rectangle. So basically you have diameter, you have a thickness of plate. You can calculate this area. Okay, so now P over T D. Sigma B, again, is average bearing stress. P is a force applied on the contact surface. A is the projected area of the contact surface. It's not a contact surface itself, it's projected area. So since it's more like a stress generated on contact surface, the sign is always positive. So there's no really, it's more like a pressure applied on the surface. It's always positive. There's no negative bearing stress. Any question here? So if no question, let's move on to a new example problem. So this is more like a combined example problem that combine all the equations we learned in the normal stress, shear stress, and the bearing stress. Yes, it's the same. We use sigma, but we have the subscript B here. So whenever you see the subscript B, it should be bearing stress. But I just want to make it clear, we don't normally calculate bearing stress a lot in solid mechanics. Normally we concerned about the normal stress, shear stress. Yeah, but this is just to be complete. So now this is the example problem that combine normal stress, shear stress, and bearing stress. And you would see that your homework or your quiz or your exam should be somewhere in this level. It's not in this level or this level, because these two example problems just like right after each concept is really help you understand what the basic equation means. But the level of difficulty in your quiz and in your homework should be in this level. So it's a steel bar that is designed to carry a tension force, magnitude, well, it's tension, so 120 kilonewton. So the force here, let's say the force here is 120. And of course, this is, you can consider, this is a front view, this is a top view, it's the same thing. Double bracket at A and B. And we have the bar thickness is given. So the thickness is this dimension. This is 20 millimeter. Maximum allowable stress, maximum allowable normal stress, allowable shear stress, allowable bearing stress. So again, normal stress, we normally use sigma. Tau is shear stress most of the time. And if you sigma subscript B, then it's bearing stress. Design the bar, determine the required value, diameter D of the bolt, the D here, and the dimension B. This dimension. Dimension B at the end of each bar, and dimension H. So this dimension, and also it's also this dimension, is the same thing. So let's do the one by one. For determining the diameter D of the bolt, what kind of stress do we need to consider? Dimension D is here. It's a diameter of the fastener. What other stress should we consider for calculating diameter D? Anyone?
Bearing stress?
Yes, bearing stress. So of course, when you have the fastener hole of the plate and the contacting surface with this fastener, there's a more like a pressure applied on the contacting surface, and then we have the bearing stress, and this is the equation we use to calculate bearing stress, and we want to make sure that it's lower than allowable bearing stress. So this is one of the criteria. Anything other than that, we need to consider bearing stress. What else? Or just bearing stress is enough?
Would normal stress need to be calculated, since the force would be perpendicular to the surface?
Normally, we would consider the normal stress generated here and generated here. So that we will be consider after we have identified the diameter, and then we can use it to calculate B and calculate H for normal stress.
Considering the thickness of plate.
Thickness plate is given. Thickness plate is given. Is 20. You don't need to design the thickness of plate. There's a answer from the chat. Yes, it's shear. So as I mentioned, here when you have tensile for the plate itself, for the fastener, it actually generates shear stress on the surface. And the same thing this bar has tensile force 120 kilonewton. For the fastener, it is shear. So you can consider this is 120, this is the shear force, and we want to make sure that the shear stress on this cross section is lower than allowable shear stress, right? So these two determine the diameter of the bolt. So let's do the calculation.
Excuse me. I'm having a hard time just visualizing the problem to begin with. Is that where the forces of P and the two F1 and F1 are? That's supposed to go where diameter D is on the section bolt.
So you just imagine this section is the fastener, right? It's a fastener through this hole. And tensile force P is tensile force in this bar. And of course, this tensile force existing in this bar is the same as the bar, the force applied from the bar to the fastener. So this is also 120. You can just imagine this one is equal to, is same as this one. Same as this one.
Got
And
it.
120 is existing in this bar, and also is a force applied by the bar to the fastener.
Got it. Thank you.
You're welcome. So now let's do the calculation of the part A. For the D, let's be clear. We need to make sure that the shear stress existing on the fastener should be lower than 100 megapascal. We also want to make sure that the bearing stress is lower than 350 megapascal. We use these two to determine the diameter D. So tau equal to V over A. What is the V we should use here?
60 kilonewtons.
Yes, thank you. Again, let's consider this is a free bar diagram of the fastener of the bolt. You have the P equal to 120. You have shear force on this cross section and on the opposite side. So the free bar diagram becomes, well, let's P minus 2F1 equal to 0. And of course, this 2F1, this F1 is same as the shear force, internal shear force of the fastener itself. These two are the same thing. And area, of course, we can write as a function of D, of diameter. So pi D square over 4. So this one should be 100 megapascal. D should be greater, equal to 7.6 millimeter.
I have a question.
Yes.
Does what kind of stress we're looking at affect which kind of cross-sectional area to use in the formula? Does that make sense? Like, since we're looking at shear stress here, we would look at the circular cross-sectional area. But
Yes.
earlier when we were looking at the bearing, the fastener, we were using the rectangular cross-sectional area.
That is bearing stress.
The bearing stress, yeah. But
Here we are
like,
checking the shear stress.
yeah. but like if you're looking at the different kinds of stress, does that affect which kind of cross-sectional area you use?
For different stress, you should use different area.
Yes. Yeah, I just want to make sure that that's
Yes, let's do it one by one. You understand better when I complete this example problem. So for the normal stress, that's why I keep emphasizing like why we should be aware that when we have normal stress is using the area that is parallel to the internal normal force, and for shear stress is you should use the area that is parallel to the shear force. And for bearing stress is actually the projected area. So for each type of stress, the area is different. I cannot just say that, oh, you should use the cross section of the circle or anything. It's really for different stress, use different area for different application.
yes, that's what I was asking about. Not necessarily like, oh, it's gonna be circular or whatever, but like
No, that's
how
not.
it's related to the force.
It's not necessarily always a circular cross section, but let's say right now I can only say for this example problem, specifically for this example problem for this shear stress generated on this fastener. Do you agree with me that this is a cross section that we should use for calculating shear stress?
Yes.
Yes. Then we're done.
Okay, perfect. Thank you.
Okay. And also, if you want to get a bonus for the attendance, you need to make sure your video is on for the entire 75 minutes.
Okay.
So this is for shear stress calculation, and for the bearing stress, we have again PTD. What value should we use P? What value should we use for TD? For calculating the bearing stress, what force should I use here? What area should I use here?
Should P be 120?
120. P equal to 120, yes. TD.
Is TD the thickness of the bar and then the diameter of the circle?
Yes, thank you. So to make sure that you guys understand, like visualize what the area actually means. So it is here. So it's the project area of this contacting surface. So this is the area we should use for calculating bearing stress. Now, this is the D, this is the diameter of fastener. T, thickness is given. You don't need to design. It's given in the problem statement. So it's DT. And of course, it has happened to be the same, like it's also problem also show the T and D, but it doesn't always happen in this way. You just need to figure out what dimension it really means in different example, in different problems. So here is the project area. So it happened to be the T and D given here. So the thickness is 20. I convert everything to meter. D. And this one should be lower or equal to 350 megapascal. And D should be greater than 17.1 millimeter. Well, since I use Newton meter, let's make it less confusing. 10 to 6, everything Newton meter. So now we calculate two value. Asking about what diameter should we, so based on considering these two diameter, which one should we use?
The smaller one.
Sorry?
The larger one.
Smaller one or larger one?
The larger one.
Okay, yeah. Be careful when you like based on two criteria, and you calculate two diameter, which one you should use. If you use larger one, it means that it can survive from this one. It can also survive from the bearing stress. It can survive both shear stress and bearing stress. Sometimes the problem statement says ask about what the minimum diameter should what the minimum diameter is. Same thing here. And somehow students get panicking. Then okay, minimum diameter, choose this one. If you choose this one, it means that okay, it's safe for bearing stress, but it will fail because of the shear stress. So even the problem statement asks what is the minimum diameter you should use, this is the one that you should use. Now,
I have a question. I think I understand why the bearing force P is 120 kilonewtons, but can you just show real quick why it is, just so I can make sure I what I think is correct?
yeah. So the best way is go back to the concept, like what is the P represent? So if you have a plate and you have fastener hole, this force, it should be the contacting. There's no concept of contact, but it's a force between this fastener and the half cylinder of the fastener hole itself. So let's say if you have a fastener here and the force between this plate and the fastener is a P, right? So now back to the example problem. You have tensile force 120 and you have fastener here. Do you agree that the 120 tensile force existing in the plate itself is equal to the force applied by this plate to the fastener? 120.
Yes.
Okay. So that's why it's 120.
Okay, thank you.
You're welcome. So whenever you feel like confused about any part, the best way is go back to the basic concept. What does this P means? This P is the force between the fastener and the plate. And back to the example problem, the force between the fastener and the plate is 120. Any other question? Okay, now move on to part B. The dimension B at each end of the bar. And it's symmetric, of course, on this side and this side is symmetric. So this is B, this is B. So how do we calculate this B? What are the stress do we need to consider?
Like
What
the
is stress?
normal stress.
Yes. Yes. So we need to consider the normal stress should be lower than allowable normal stress. And for the normal stress calculation, we need to consider this area. Oh, wait a second. Plus this area, right? The normal stress generated on these two area. And make sure that the normal stress generated here is lower than 175. So for B, the B dimension determined by the normal stress at both location. How to calculate this sigma? Let's focus on alphabet. let's say since it's symmetric, let's only focus on this area. So what is the force should I use? What is the area should I use? What is the force should I use?
1
60.
half P.
Yes, 60. Thank you. Let's use 60. Area. Well, this is T times A. And in the end, the B should be equal to double A plus D, right? Let's calculate A first. T is 20 millimeter times A. So this one should be smaller or equal to 175 megapascal. And we calculate A should be greater than So now B dimension should be equal to double A plus D. Any questions so far?
I have a question.
Yeah.
So the area, in which calculating the normal stress, actually, when we calculate the normal stress, why is it 1 half P? Are we only calculating one of the squares, not both of the squares at the same time?
We can use either method. I know what you mean. Let's say I originally do this area plus this area, right? So, and of course it's symmetric. This one equal to this one. So that's why the one I put here is the force that applied on this single area equal to half the P. And the area I use, again, this area. But of course, you can also do it in this way. It's also correct, equal to P of, now I consider here plus here. So if I consider these two at the same time, the tensile force applied carried by these two area becomes the P. And now I divide by two area. In the end, you get the same answer. Make sense?
Do we have, okay, will we have to multiply the allowable stress? Do we have to modify that by anything, or would it stay the same?
It's this allowable stress is always the same.
Okay.
Allowable stress, let's back to what I said in the introduction part of mechanics materials. Stress is about force per unit area. So as long as we are using the same material, allowable stress should always be the same. It's allowable stress determined by the material itself. So let's say if you use aluminum 6061 or 7075, as long as it's that specific material, allowable stress is always the same. And that's why we keep saying like to determine a structure will fail or safe is not about the force. The force can be half, can be doubled if you consider different area, but the stress is always force per unit area, and we compare it with allowable stress. Allowable stress doesn't change. So if you consider this area plus this area, then this becomes 120 and 2 times 0.02 times A. And this one smaller than equal to 17526. And you get the same thing.
Okay, thank you.
You're welcome. Any other question?
Sorry, I'm kind of lost in terms of how I know A equals 17.1 comes from the bearing stress we calculated before, but how does that relate? Like, I'm not understanding how we're using what we determined before for this example.
A is not from bearing stress, A is from normal stress. So we need to determine the dimension B, right?
Yeah.
We already determined the dimension D in the first step based on our shear stress and bearing stress. We already have the defined D value. So to determine the dimension B, the only thing we need to figure out is this dimension.
Oh, so they just happen to be the same number for
Yes,
the
happen
bearing
to.
stress and
It's
oh, okay. Okay, all right.
accidentally the same.
Okay.
Any other question? Yeah, so somehow this is accidentally the same as this one. I'm not adding this one double to this one. No. Ignore this one for now. So this is diameter we confirmed from the first step calculation. This is the A dimension we calculated from the normal stress at the border section, and we have doubled A, which is 17.1 plus D. We calculate in the first step 27.6. Any other question? Okay, now let's move on to the third step. For dimension h, we need to determine the dimension h here. So what stress do we need to consider? What stress do we need to consider for calculating shear? Normal.
Great.
Why shear for the normal?
For the bar, like when it's going like this, breaking, or are you like that?
I'm not quite understand like this like that. Could you please explain?
How is it breaking?
That's the question I'm asking you. How's it breaking? Yeah. So I just want normal is easy to understand. We need to consider normal, but this one answer is about shear. Why do we need to consider shear for determining h? That's my question.
We can get area.
Sorry?
So we can get the area. So we can have H, wouldn't H be the area so we can have the thickness?
Is there shear stress generated in this plate, in this bar? No. Shear stress is generated in, so let's say for this fastener, you have a force applying this way and corresponding force applied by the pin joint in this way. So for the fastener, this is a shear stress, but in the bar itself, it's tensile. It's tensile. This for the steel tie bar. For the bar itself, it's really only tensile. There's no shear stress. Shear stress is generated in the fastener because for the fastener, this tensile force in this direction is becomes the transverse force for the fastener. But for the bar itself, it's only tensile. So it's only normal stress. Make sense or not? So now we know that for this structure, for this steel tie bar, it's only tensile force, and we need to calculate what is the normal stress generated in this cross section, which is equal to 20 times h. And of course, the internal tensile force should be 120 kilonewton. And this one should be lower than 175. This is how we determine h. Makes sense or not? Okay, now let's do the calculation. oh, actually, this is a better picture to show. So tensile force 120. This is the H. This is the T. This is the cross-section area we need to use to calculate the normal stress. It is normal stress, it's not shear. So to determine the H, we need to consider the normal stress at midsection. So sigma equal to P over TH. So 120 H 175 10 to 6. So H should be greater equal to any question?
I have a question. Just to be clear, we'll just the reason we're finding H is where we know the appropriate thickness. This needs to be so that it won't fail.
B is this two does not affect. So B is this dimension. B is this dimension.
Not V, I mean H.
H.
We found H, so it's thick enough so that when we apply 120 kilonewtons of force, it won't fail.
Yeah.
Okay.
Yeah. So basically, for determining the H, the only stress that would cause it to fail here is a normal stress. And so what we need to do is that we calculate what is the actual normal stress generated on this cross-section and make sure that the normal stress generated on this cross-section is lower or equal to the allowable normal stress of the material. So we have this equation. So this equation is to make sure that the middle section part of the bar will not fail because of normal stress. And you also can see that for the normal stress, we actually check two cross-section area. One is here in the step C, and in step B, we checked here. Right. So we want to make sure that, okay, it will not fail here or it will not fail here because of normal stress. Any other question? We can move on to the next topic. We have 10 minutes. Is there any question for in exam quiz? Would those extra figures be given? No. These figures are given here because it's easier for me to explain to you why do we need to use those cross-section for calculation. But in the exam and quiz, you will be only given this part. You need to figure out what is the D, what is the B, what is the H, and when to use which dimension for calculating which stress, and what is the critical stress at a certain cross-section. Any other question? Okay, let's move on to a new topic. Wait a second. You can check the new lecture note I post in file. Let me switch to the other one. So the new topic is the stress on the oblique plane under axial loading. So what we have talked about in the first section is always about the normal stress on the cross section. An area that is perpendicular to the axial loading direction. But we do have situation that what if a structure has a joint? Let's say you have two beam and this is a glue joint or use fastener. And let's say this is the welding joint, and this welding, this surface itself, it's not necessarily perpendicular to the loading direction or the x direction of the bar. In this situation, this direction is not necessarily perpendicular. So there it becomes an inclined angle, and it's so we want to check that if it's safe on this plane. The content we have learned is if it's safe on the cross section of the structure, now we need to check on this, let's say this weld joint or the glue joint, if it's safe. So the topic is stress on the oblique plane and axial loading. I think this is chapter 1.3. So in this situation, let's say on a inclined plane, in general situation, let's simplify in this way. Let's say you still have 1D bar and you have actual tensile force applied. And we want to figure out on this inclined plane, let's say this inclined plane has the theta angle to the original cross-section area, theta angle to the vertical direction. So we want to figure out what the normal stress and shear stress on this inclined plane. So let's say for the welded joint or the glue joint, if I give you for the glue joint, what is the allowable normal stress and allowable shear stress on this glue joint, you can decide if it's safe or fail on this glue joint. So let's say for this force applied, we can resolve into two components. One is the normal force that is perpendicular to the inclined plane. And one is the shear force that is parallel to the inclined plane. Yeah. So let's say that this inclined plane is the A theta. So N becomes the normal force to the A theta. And V is the shear force to A on the A theta, the inclined plane. And this A theta, of course, if you check, this is A theta plane, and this is the cross-section area. So the relation between these two areas is, let's assume that the cross-section area is A naught. So A theta times cosine theta. If consider this is the cross-section area is A naught. And this one equal to A theta times cosine theta. Oh, yes, sorry, this is just V. Thank you. Normal force, shear force. Normal force perpendicular to the area, shear force parallel to the area. Back to our first lecture again. So now to figure out the normal force and the shear force, again, N should be equal to P times cosine theta. V equal to P times sine theta. So this is theta. Now, for the normal stress and shear stress on this inclined plane, based on our definition we learned, it's the normal force of the A theta should be equal to P cosine theta A naught cosine theta. So it's P A naught cosine theta squared. And tau, shear stress is the shear force over the inclined area, which is P sine theta cross-section area cosine theta. So now this becomes P A naught sine theta cosine theta. Let's make it clear. So the cross-section area here, oh, this is A naught. So that's why we have this equation. Any questions so far? So the basic idea that for the shear stress and normal stress on this inclined plane, we need to figure out what is the normal force on the inclined plane. What is the area of the inclined plane? For shear stress, we need to figure out what is the shear force on the inclined plane and what is the area of the inclined plane. So basically this is written in terms of the force P applied, we resolve into the perpendicular to the plane direction and parallel to direction to the inclined plane direction. And for the area, if we define the cross-section area is A naught, then we have the relation that A naught equal to the area of the inclined plane times cosine theta. And everything is solved. Where does A theta cosine? So if you let's move to here. Let's move this one here, and let's only focus on here. Do you agree that if this one equal to this angle equal to theta, a naught equal to a theta times cosine theta? Right. This is clear. Did I answer your question? Okay, great. Any other question?
Can you say that?
Sorry?
Can you repeat that last statement?
It's a relation between these two?
Yes. Oh, okay, I get it now. I'm sorry.
Yeah, it's fine. So the cross-section area, which is the area that is perpendicular to the actual direction, we put as a naught. And the inclined area, we use a theta. And the relation between these two is the a naught equal to the a theta times cosine theta. Any other question? So if no question, we are done for the class today. Thank you for coming and have a great weekend. If you have any question about the homework or the class content today, please come to my office or I will change to the office on Zoom link very soon. Thank you.
Thank you.
You're welcome. Have a great weekend. Shear, this one? Okay, yeah.
Can I ask a question?
Yeah.
So a naught is like the cross section. A naught is the cross section, and a naught cosine is like it would be the cross section angled upward.
A theta cosine theta.
I mean, yeah, wait, say that again.
A naught equal to a theta cosine theta. This one equal to this one times cosine theta.
Okay.
Right. It's not a naught times cosine theta. No, it's this one times cosine theta equal to this one.
So where we get a theta from?
Now we can write in the way that in the equation when we need a theta, we just write it as a naught cosine theta, right?
Mhm. Oh, we know a naught.
Yeah, because normally you would know that what is the cross-section dimension, you would know that what is the angle between the inclined plane and the cross-section area. So these are the given information. We need to use those to calculate the a theta. Right?
Oh, okay, I get it. So like we know, like if we had like a cube, we know the area of the cube, and then we
Yes.
had it
So
cross
let's say,
section.
yes, let's say as a structural engineer, the information to give you is, let's say I have a bar. The information to give you is, okay, what the length of the bar, what the cross-section dimension of the bar. And I have inclined plane, I give you the angle to this vertical directional angle to the actual direction. And then you solve everything on this inclined plane. But normally you don't give the information of what the area of the inclined plane, what is the normal force, and what is shear force on the inclined plane. That is one you need to be calculated from the actual force and cross-section dimension. Make sense or not?
It does. Thank you.
You're welcome.
Sir, can you hear me?
Yeah.
I had a question. Why do you, like, when you're solving the problems, I've noticed you put like greater than and less than. Why do you do that? I'm just curious. Is there like a specific reason why?
Sorry, could you please repeat the question? Why did I what?
Like when you like solve for like the stuff, you put greater than or less than, like you put D is greater than or equal to 27.6, like stuff like that.
Oh, okay. Is the example problem in the previous lecture?
Yeah, or
Okay.
like just now you
Yeah.
were doing the example earlier. You
Yeah.
put D's greater than or equal to 27.6.
What is your preferred way to solve that?
Well, no, I don't know. I'm just curious, like, why do you not just put like equal sign, like D's equal to 27.6? Like, does it matter or no?
Doesn't matter, doesn't matter. Both are fine. So you can, because we are calculating a threshold value, right? You can use equal to, you can use greater, or you can use greater or equal to, doesn't matter, as long as we find the threshold value.
Okay, I assume so. I was just curious because I saw you were putting it down a lot, like when you were writing down the equations, you were just putting down like V over A is equal to like the T, which is less than 100.
Yeah, yeah,
Just like just put it equal to instead of a less than stuff.
yeah, yes, yes.
Okay,
It doesn't
cool.
matter, yes.
I just wanted to double check. Okay, thank you. That was all.
Yeah.
Hi, I had a quick question about something with the homework. So I made a mistake and I accidentally, when I submitted it, I only submitted my work for the second question. And like I did all of it. I was just wondering if I could like email you or TA the full work because I just forgot to submit the first question. It was just like a careless submission error and I would really appreciate it.
You can email me but I will put on hold because let's say if this is the only time for the whole semester, I will ask TA to grade the first problem at the end of semester. But if it's like happen multiple times, yeah.
Okay. Yeah, I understand. I'll make sure this doesn't happen again. It was just an honest mistake. I was submitting and I just like totally forgot. I was like working on this question two at the end and I just like
Yeah.
only submitted that
So
one.
for the future assignment, you just need to make sure that you always double check your submission. Otherwise, it's well,
Yeah,
yeah.
absolutely. Thank you
Yeah.
so much. Should
So
I send it to you? Huh?
email to me and I will put on hold until the end of semester. If this is like only one time in the whole semester, I will ask TA to grade.
Perfect. Thank you. Would you like me to email it to you to your email or on Canvas?
Not use Canvas, only use my DTI and GUFL email. Yeah.
Okay, perfect. Thank you so much, Professor Dong.
You're welcome. Have a great weekend.
Thank you. You too. Bye-bye.